welcome everybody for the second day of this workshop. We will have the second of these 1 hour talks that Anush mentioned yesterday. This one will be given by Ben Rossman, who is from Toronto and well known for his exciting work on circuit complexity and finite model theory. And today we'll talk about lower bounds for subgraph isomorphism and consequences of first-order logic.
Okay, well, let me first of all thank the organizers for the opportunity to speak here. So today I'll be talking about some recent work in circuit complexity on the subgraph isomorphism problem and some corollaries in finite model theory. So here's kind of outline of the talk. I'll start by introducing the subgraph isomorphism problem. I'll give some background on circuit complexity and the connection between AC0 and first-order logic. Then I'll discuss the main results, which are upper and lower bounds for this subgraph isomorphism problem. And we'll see that there's a connection between AC0 circuit size and the first-order, the variable width in first-order logic and the tree width of the pattern G. And for formula size is a connection with quantifier rank and tree depth. So I'll define all this as we go along. And then finally, I'll discuss a really neat connection between this circuit lower bounds and a result in finite model theory. So let me start off by defining the subgraph isomorphism problem. And I'll begin with two important examples. So the first is the k-click problem. So here, k is some fixed parameter. And we're given as input a graph x. And the question is, does it contain a k-click, so a complete subgraph of size k? So the k-click problem is extremely important in complexity theory. So as for its time complexity, so there's a brute force upper bound of order n to the k simply by searching over all possible k-clicks. Somewhat better upper bounds are known using fast matrix multiplication. You can get n to some constant less than 1 times k. But it's believed that n to the omega k is really a lower bound for this problem. And if you could prove this for all k, or even for any growing sequence of values k, then you would separate p from np. So k-click's a very important problem. Another example of a subgraph isomorphism problem is the distance k connectivity problem. So here the input is a directed graph x with distinguished vertices s and t, and the question is whether s contains an st path of length k. This is also an important problem in complexity theory. So if we look at, say, the space complexity of a distance k connectivity, so the best known upper bound from Savage's algorithm is order log k times log n. And it's believed that this is optimal. So if you could prove a matching lower bound, then you'd separate complexity classes L and NL. Okay, so let me now introduce a general subgraph isomorphism problem. First, I'll introduce a sort of uncolored version, which is maybe what most people would mean by subgraph isomorphism problem. So we have some fixed graph G. And the input, again, is a graph x on n vertices. And the question is, does it contain a subgraph isomorphic to G? So by subgraph, I mean not necessarily induced subgraph. And I'll denote this by sub-uncolored of G. But the more important problem for this talk will be the colored version of the subgraph isomorphism problem. So now we imagine that we're given a graph x as well as a coloring of vertices of x by vertices of G. And now we're asking if x contains a subgraph which is isomorphic to G via the coloring. And as we'll see, this is a much more well-structured problem. Okay, and really these two problems I introduced before can be seen as special cases of this colored subgraph isomorphism problem where the pattern graph G is either a complete graph or a path of length k. Okay. So let me mention some reductions between these problems. So first of all, there's a very well-known reduction from the uncolored problem to the colored problem by the so-called color coding technique. In other words, if you could solve the colored problem, then you can solve the uncolored problem with just a small log blow up in time. For many graphs G, these two problems, the complexity coincides. So in particular, when your graph G is a core, meaning that every homomorphism from G to itself is 1-to-1. An example would be if G is the complete graph. One important feature that the colored problem has that the uncolored problem lacks, well, we believe it lacks is minor monotonicity. So whenever your graph f is a minor of G, then there's a reduction, in fact, a linear size monotone projection from the f subgraph isomorphism problem to the G subgraph isomorphism problem. I'm going to come back to this toward the end of the talk, so let me not define what a minor is now, but just to mention that. So this is a feature of this problem that will play an important role later on. Okay, so here's the summary so far. So this G subgraph isomorphism problems are an important and well-structured family of problems. As we'll see, the complexity of this problem is tied to natural structural parameters of the pattern G. And determining the complexity of this problem with respect to different computational resources, such as time and space, if we believe that this is in fact tied to these parameters, then we'd separate complexity classes P versus NP, L versus NL, and so on. Okay, so this is. Okay, so of course there are many computational resources that one could consider, and so for the rest of this talk, I'm going to focus on circuit size and formula size. Okay, so the next slides will give a sort of overview of circuit complexity. So Boolean circuits and formulas. So by Boolean circuit, I mean, so we have and, or, and not gates, sort of without loss of generality, nicely layered like this, and we have our inputs at the bottom and negations as well. Okay, so for purposes of this talk, you can think of circuit size. So the circuit size of a Boolean function is the fewest number of gates you need to compute that function. And this complexity measure of Boolean functions is essentially equivalent to Turing machine time. Okay, so there's an asterisk here. This is up to a polynomial factor and ignoring uniformity. But this lets us sort of frame the P versus NP problem in terms of circuits. So we can think of P as the class of problems solvable by polynomial-sized Boolean circuits. NP is the class of problems whose solutions are verifiable by polynomial-sized Boolean circuits.
So what, I mean, why not give it the real name? It's P/poly.
It's P/poly, but
Okay, but they're not equal. Yeah. So, okay.
No, sure. Okay, so ignoring uniformity. Okay, so the holy grail of circuit complexity, anyway, so a path to showing P not equals NP, would be to show that any problem in the class NP, for example, the maximum click problem, requires superpolynomial circuit size. So in fact, we believe that maximum click requires exponential circuit size. But a sort of parameterized approach to, so the sort of minimal way that you could get a superpolynomial circuit size lower bound would be by proving a sort of sequence of increasingly stronger polynomial lower bounds. So if you could show that k-click requires circuits of size n to the omega k, which we believe is the case, for any increasing sequence of k's, then you would separate P from NP. Okay, but unfortunately, circuit lower bounds are hard. So this is showing the sort of world record circuit size lower bounds for explicit functions in the class NP, and as you can see, progress is quite slow. So currently the best lower bound is only 5n. Okay, so in order to even prove superlinear circuit lower bounds, we need to focus on weaker models of computation, and for this talk that will mean restricted classes of Boolean circuits. Okay, so the one very nice restricted class of circuits are Boolean formulas. So formula is a tree-like circuit, so a circuit with the structure of a tree. In other words, every gate has fan-out 1. And intuitively, formulas are a weaker model of computation in that they're memoryless. So the result of each subcomputation is used only once. Okay. So we believe formulas are weaker than circuits. But this is, in fact, sort of an open problem. And this is another holy grail in circuit complexity. This would be equivalent to separating complexity classes NC1 from P. The challenge is to show that any explicit problem in the class P, such as ST connectivity, requires superpolynomial formula size. Okay? And once again, this subgraph isomorphism problems give a nice parameterized approach to this problem. So if you could show that distance k connectivity requires complexity n to the omega log k for any growing sequence of k, then you would separate NC1 from P.
So can I ask you, I'm sorry to bug you about this, but from now on, should I assume that every complexity class is actually the non-uniform version? Is that?
Yeah, for this overview, that's fine. It's yeah. Okay, so once again, we're in the unfortunate situation that, formula size lower bounds are also quite hard. And so here's the world record formula size lower bounds for explicit functions in the class P. And here at least we have polynomial lower bounds, but we get stuck at cubic. Okay, so it's a similar situation. And so once again, if we want to be able to prove unconditional superpolynomial lower bounds, we again need to focus on restricted classes. So sort of for the rest of this talk, I'm going to restrict attention to a particular restricted class of circuits and formulas known as AC0. And these are Boolean circuits and formulas of constant depth. So you have just some constant number of layers of AND and OR gates. And of course, you allow unbounded fan-in to your gates.
Before you leave the general case, I want
Sure.
to ask you, you personally, do you believe that something can be done? Because it's possible that all these separations cannot be done, say, within Peano arithmetic.
So for formula lower bounds, I'm optimistic that we can that we can do something. I wouldn't even wager to guess about circuits. Yeah. Okay, so I mean there are other restricted models that one can look at. You could look at the monotone case, but here we'll be looking at constant depth. Okay, and what I'll show next is that so AC0 circuits and formulas are an interesting class in their own. As Neil mentioned in his talk yesterday, they model what you can do in constant time with sort of polynomially many processors. And they also have very nice connections to logic. So let me explain that next. Okay, so there are close connections between AC0 and first order logic. Okay, so there's sort of two resource measures of first order formulas that we look at in this talk. So one will be the what I'll call in this talk variable width. So this would be the maximum number of free variables in a subformula. So people often talk about the k variable fragment of first order logic. So that's what they mean. So this gives one hierarchy within first order logic.
Is it the same as if you allow reusing variables?
Yes, yeah, good point. Yes, this would be the same thing as you only have k variable names in your sort of vocabulary, and you're allowed to reuse variables. That would be FO superscript k.
Yes, I really like this. It's a more elegant definition. So you don't have to reuse the variables. It still gives.
Right. If you haven't seen this before, yeah, maybe. Anyway, so those are equivalent. And another sort of complexity measure of first order sentences is quantifier rank. So this is the nesting depth of the quantifiers in your formula. Okay, and so these have very nice connections with AC0. So here's the kind of basic theorem on it. So you have a first order sentence phi. So the model checking problem for phi is the following problem. You're given a structure with universe 1 to n, and you want to know, is A a model of phi? So the basic theorem is that this is solvable by AC0 circuits of size order n to the variable width of the formula. And this is essentially an exercise. You just, each existential gate, you make a big an OR gate. And okay, so the observation here is that, so the depth of the circuit, well, you're only going to have quantifier rank many layers of unbound of the big fan-in gates, but those will all have fan-in n, because each quantifier is quantifying over the universe of size n. So if you were to take these circuits and transform them into formulas by just making them tree-like, then so the formula size is sort of bounded by depth times fan-in. So we can also say that the model checking problem is solvable by AC0 formulas of size n to the quantifier rank. So this is the connection between circuit size and variable width and formula size and quantifier rank. And of course, quantifier rank is always at least variable width. Formula size is always at least circuit size. Okay. And just briefly to mention, another kind of resource hierarchy within first order logic would be, sort of with respect to background relations. So you could allow so you have vanilla first order logic, and since we're always talking about finite structures with universe 1 to n, you could also consider the setting where you have in the background a linear order or a bit predicate, or even arbitrary relations, which sort of correspond to non-uniform AC0. So sort of get to what so Neil was hinting at this distinction before. So if you look at first order logic with a bit predicate in the background, then so this nice results in descriptive complexity show that this corresponds to uniform AC0. But for what I'll be talking about, really, our lower bounds at least will apply to the non-uniform AC0, which corresponds to first order logic with arbitrary background predicates. Okay, I don't want to say too much more about this. Okay, so just the takeaway from this part of the talk, we have the following. So here's how you can get results in lower bounds in logic from lower bounds in circuit complexity. So lower bounds for AC0 circuit size translate into lower bounds on the variable width, the number of variables you need in first order logic with arbitrary background predicates. And lower bounds for AC0 formula size give you lower bounds on quantifier rank. Okay. So, okay, good. So now let's get back to the main subject of our talk, the subgraph isomorphism problem. So I'm going to present both upper and lower bounds for this in terms of these natural structural parameters of the graph G. So let me start by showing you what are the upper bounds. Okay, so the theorem, I don't know if anyone knows what the attribution for this, let me know. But so it's not hard to show that this G subgraph isomorphism problem is definable by first order sentence with tree width plus 1 variables, and as well as by first order sentence with tree depth quantifier rank. So I'm going to define what these tree width and tree depth are next. But and moreover, you can do this with first order expressions which are existential and positive. If you translate these first order formulas into AC0 circuits and formulas, you get AC0 circuits of size tree width and formulas of size n to the tree depth. Okay, so let me define things a bit. So tree width of a graph G is defined in terms of a notion called a tree decomposition. So here we have a graph G, and the tree decomposition of G is a tree whose nodes are labeled by subsets of the vertices of G such that some condition holds. So if you look at any vertex here, or I guess every edge belongs to some bag here, and the set of nodes of the tree which contain a given vertex such as B is a connected. Okay, so this is a tree decomposition, and tree width is defined as the essentially the size of the bag you need here minus 1. Okay. The definition actually isn't really so important for the talk. Just to mention, so that if you have a tree, any tree has tree width 1, and the complete graph has tree width k minus 1. And to get the upper bound for subgraph isomorphism, you note that if you have any width k tree decomposition for G, it kind of gives a blueprint for a k plus 1 variable first order sentence which defines the presence of a G subgraph. This is more or less an easy exercise. Okay, as for tree depth, this may be a somewhat less familiar notion to people. So let me first define the notion of the closure of a tree. So T here is a finite rooted tree, and the closure of T is the graph formed by adding edges between all ancestor-descendant pairs in the tree. So in other words, you put a click along every branch of this tree. So that's the closure of a tree. And the tree depth of a graph G is the minimum height of a tree T such that G can be realized as a subgraph of the closure of T. Okay, so just to illustrate this with a few examples, the tree depth of a complete graph, let's say K4, is 4 because it's actually equal to the closure of the path of length of order 4. The complete bipartite graph K33, this is showing that, well, it's actually, I guess, the closure of this graph here. And for paths, the tree depth is logarithmic in the order. So this is showing that P7 here is a subgraph of the closure of the complete binary tree of height 3. Okay, so this is tree depth. So there's some just to mention some relationships between these parameters. So the tree depth is always at least the tree width, and at most the tree width times log number of vertices. And also it's sort of exponentially related to the length of the longest path in the graph G. Okay. And similarly to what we had before, so if I give you a height k tree, such that G is a subgraph of its closure, you could take this as a kind of blueprint for a quantifier rank k first order sentence which defines the G subgraph problem. So it's an easy exercise to sort of show that this is giving an upper bound. Okay. So let me now state the main results of the talk, which are going to be matching lower bounds for AC0 circuits. Okay. So these are the two main results that I'll say something about in the rest of the talk. Okay, so the first is that, so this is joint work with Yuan Li and Alexander Razborov. So the result is that the AC0 circuit size of the G subgraph isomorphism problem is n to the omega tree width. So this is really tree width over log tree width. I'm just hiding the log factor. Okay, so this is almost matching the n to the tree width upper bound. Okay. Oh, and then the second result, which is in the recent joint work with Kenichi Kawarabayashi, we get similar matching lower bounds for the AC0 formula size of sub G. We show that this is n to the omega poly tree depth. So tree depth to some fixed constant epsilon. Yeah?
This is quantified over all graphs?
Yeah, overall, this is for all graphs, for all fixed graphs, right? Okay. And to mention, so both of these results sort of extend special cases, which I showed in previous work. So, so this result here is sort of generalizing the technique of my earlier work, which shows that the k-click problem has AC0 circuit size n to the omega k. And this theorem here is sort of building on earlier work, which shows that the distance k connectivity problem has AC0 formula size n to the omega log k. So these are both sort of special cases of these things. So as corollaries in logic via this connection that I described earlier, it follows that the sort of variable width of sub G is omega tilde of the tree width. And the quantifier rank you need to define sub G is polynomial in the tree depth, even with arbitrary background predicates. Okay, so this is just translating these circuit lower bounds into the first order logic. And each of these also kind of resolve questions which had been asked in finite model theory. So a sort of corollary of this result, even just for k-click, this shows that the variable hierarchy is strict over ordered graphs. So this had been an open question. And sort of an interesting corollary of this result, which came as rather a surprise to me, that this gives a new proof of this homomorphism preservation theorem on finite structures, and in fact with a much better parameters. And so I'll get to that at the very end of the talk. So just to explain where is this coming from. So sort of corollary of this result, so the k-click problem, of course, is definable with just k variables. You don't need any background predicates. But what this result shows is that on ordered graphs, or even with a linear order in the background, or even arbitrary background predicates, you need at least k over 4 variables. So this shows that the hierarchy is, I guess, non-collapsing. And then a very nice observation of Neil Immerman showed that implies that the variable hierarchy is strict on ordered graphs. Okay, so I'll tell you, in the rest of this talk, I'll say something about the proofs of both of these results. So let me start with how we prove this result here. And the proof uses a probabilistic method. So what we really show are average case lower bounds with respect to particular input distributions, so particular random input graphs, which are sort of generalizations of the Erdős-Rényi random graph. And I won't say too much about the actual proof technique, but I want to tell you what the sort of hard on average input distributions look like and how they're related to the tree width. It's one of the, yeah. Okay, so let me say something about that. And let me start off by talking about what's the average case for the uncolored subgraph isomorphism problem. And here there's a very natural distribution of input graphs to look at, which are the Erdős-Rényi random graphs. So Erdős-Rényi NP. So this is the random graph where you have n vertices, and for each pair of vertices you put an edge independently with probability p. So, so for every fixed graph G, there's some kind of threshold value for the appearance of G subgraphs. So, I mean, here if you plot out, I mean, here's this edge density P, and then the probability that the Erdős-Rényi random graph contains a subgraph isomorphic to G, this is an increasing function, so there's some unique threshold value where this probability is exactly 1/2. So that would be a very natural random input to look at. And sort of remarkably, it turns out that for many graphs G, so in particular for the K-click problem, the random graph at the appropriate threshold turns out to be a source of, or we believe it's a source of hard on average input distributions. So yeah, it's sort of a remarkable phenomenon. So what's the average case now for the colored subgraph isomorphism problem? And now there's no longer one canonical choice of sort of product distribution which you could look at, but rather you sort of get a family of input distributions which you might call G-colored Erdős-Rényi random graphs. So we're kind of going to allow a different edge probability for each color class, for each pair of color classes. And there's a really nice characterization of what the what is a threshold for these random graphs. So let me just tell you.
What does hard on average mean here?
Okay, so I mean, so it's conjectured that okay, so let's just talk about the uniform random graph Gn 1/2. So we know that you know, almost surely the largest click has size roughly 2 log n, but it's a very big open problem actually raised by Karp to find a click bigger than bigger than log n, so bigger than half the expected size. So we believe that this is hard instances for the click problem.
I see. So there's no expected polynomial time algorithm.
Right. Yeah. Okay. So as I mentioned, the idea is we're going to allow different edge density for each pair of color classes in these colored random graphs. And the question is, what's a sort of threshold family of these densities? So there's a really nice characterization of this class. Yeah.
The color classes will be of the same size?
Yeah. So I'll show in a second. Yeah. So let me introduce a notion which I'll call a threshold weighting for a graph. So so a threshold weighting is so for each edge in the graph, we have a function beta which is assigning a value between 0 and 2, and we'll say that this is a threshold weighting if it meets 2 conditions. So the first is that for any subgraph of G, if you look at the sum of the edge weights in that subgraph, it's at most the number of vertices in the subgraph. And the second is that this inequality holds with equality in the case where f equals G. So in other words, the sum of all the edge weights in the graph equals the number of vertices in the graph. So here's one example. If you add these 4 edge weights, we get 4, which is the number of vertices. But if you look at any subgraph, the sum of the edge weights is always at most the number of vertices. And there's a really nice alternative kind of characterization of this class, which comes from Markov chains on the graph G. So Markov chain, you have sort of transition probabilities supported on the edges of the graph, which the transition probabilities coming out of any edge sum to 1. Okay, so for any Markov chain supported on the graph, this induces a threshold weighting by just taking the sum of the transition probabilities in the 2 directions on the edge. So yeah, every threshold weighting can in fact be realized by some Markov chain. It's not 1-to-1, but this is another. Okay, and here's the connection between. So just to mention briefly now, there's a nice connection between these Markov chains on a graph and tree width. So just to say this somewhat informally, but so if for any graph G with tree width k, there exists some set of vertices of size omega k, and some Markov chain on G that concurrently routes 1 over k log k flow between all pairs of vertices in S. So, okay, the precise meaning of this statement is not terribly important. Just to point out that somehow this is a kind of dual. A certificate of having large tree width is always the existence of a certain kind of flow, concurrent flow or Markov chain on the graph. And we're going to use these as the construction of our good threshold weightings. Okay. So let me now define. So for any threshold weighting beta, we get a G-colored random graph, which I'll denote x of beta, just in the following way. So we're going to create a cloud of n vertices for each of the vertices of G. And then we put edges, for every pair of edges between a color class, we put an edge, independently with probability n to the minus beta of the edge. Okay, so the random graph might look like this. If beta was 1, then you get something which looks more or less like a random matching. Okay, so these are the random graphs corresponding to the threshold weightings. Okay, so these have a lot of really nice properties. So justifying the terminology threshold weighting, you can show that this x sub beta, the probability that it contains a G subgraph is bounded away from 0 and 1. And moreover, in sort of nice cases when G is connected and this beta is strict in some sense, that the number of G subgraphs is asymptotically Poisson. And there's a really nice expression for the number of F subgraphs in here for any subgraph F of G. Okay. This isn't terribly important, but we use all these facts about this random graph in the lower bound. Okay, so I'm not going to wade too much into details of how we prove this, but just to show this kind of sketch here. So, okay, so the result is that AC0 circuits for the G subgraph problem require size n to the omega tree width over log tree width. So there are 3 steps. So first is we define some constant C of beta associated with each threshold weighting beta. Okay, and then we sort of the main result in some sense is we show that the average case AC0 circuit complexity of the G subgraph isomorphism problem with respect to this input distribution is really characterized by this constant C of beta. So we get actually both upper and lower bounds. So a lower bound of n to the C of beta and an upper bound of n to the 2 C of beta. So this parameter is really characterizing the average case complexity. And then the third step is showing that for every graph G, there exists some threshold weighting with the property that this C of beta is at least the tree width over log tree width. Okay, now if you combine these steps 2 and 3, or the lower bound from here and step 3, then we get our theorem. Okay, so that's how this goes. And and of course this beta is coming from this Markov chain that's a kind of certificate of having large tree width. Okay, so now I'll say something about the second result, so this lower bound on the AC0 formula size in terms of the tree depth. So let me remind you of the definition of tree depth. So recall that the tree depth of a graph G is the minimum height of a tree T such that G can be realized as a subgraph of the closure of T. Okay. So we're now going to really exploit this minor monotonicity of the colored subgraph isomorphism problem. So I mentioned this earlier, but let me say it in somewhat more detail now. So first of all, what is a minor of a graph? So here we have a graph G. So a minor of G is any graph you can obtain from G by first you can throw away some vertices and edges, and then you can take sort of disjoint connected subgraphs in G and contract them into single vertices. So this is showing that this F is a minor of G in that way. Okay. So whenever F is a minor of G, there's a reduction from the F subgraph isomorphism problem to the G subgraph isomorphism problem. This is a fairly easy exercise, and these reductions are actually it's really a linear monotone projection, in fact, from this problem to this problem. Okay, so that means that the complexity of this F subgraph isomorphism problem is always at most the complexity of the G subgraph isomorphism problem. Okay, so so these parameters, tree width and tree depth, have the nice property that they're monotone with respect to this graph-minor relation. So if f is a minor of g, then the tree width of f is always at most the tree width of g, and similarly with tree depth. Okay, and so there's this celebrated Robertson-Seymour graph-minor theorem shows that every minor closed class of graphs is characterized by a finite set of excluded minors. So in particular, if we look at the class of graphs G with tree depth at most k for any constant k, this is characterized by some finite set of obstructions. But it's known that the size of this set is doubly exponential, or at least doubly exponential as a function of k. So the question is, well, suppose we only want to approximate tree depth. So we want a sort of set of obstructions which give an approximation of tree depth. Can we get away with some sort of fixed set, which is independent of k in some sense? So just sort of for example, if you recall earlier in the talk, I showed that the tree depth is sort of exponentially related to the length of the longest path. So log of the length of the longest path is always at least the tree depth, which is always at most the length of the longest path. So the longest path is sort of an exponential approximation to tree width, and this is really just 1 plus the largest excluded path minor. So if you just look at excluded path minors, that's giving you some approximation, but it's only exponential. Okay, and what we're going to want for our result is a polynomial approximation of tree depth. So in the case of tree width, this was accomplished actually recently by this sort of polynomial grid minor theorem of Chikuri and Chisoi. So the result is that every graph with tree width at least k to some fixed constant contains a k by k grid minor. Okay? And moreover, the k by k grid minor has tree width k. So this is showing that the set of grid minors, so the largest grid minor in a graph, is a polynomial approximation of its tree width.
But what's grid minor?
Oh, so a k by k grid. So you want to know the largest k, such that the k by k grid graph, is a minor of your. Yeah.
C depends on what?
No, so C is an absolute constant. In their proof, it was, I think, 86. It's known that the best it could possibly be is 2, so this will never be a linear. So this will always be a polynomial approximation, but yeah. And I mean, I guess I should say that the original grid minor theorem of Robertson and Seymour had some exponential bound here in terms of k. And so this has been a big open problem in this graph minor theory.
Does it tell you how to find the k by k grid minor? No.
In fact, it does. So their result, in fact, gives a polynomial time algorithm which finds the. Is that right? No, I guess that.
Finding a minor for a fixed graph is a polynomial time problem by Robertson and Seymour. So.
Right. Well, okay. I know that it's effective in some sense. I don't want to say something too strong, but I believe it does give.
So in your results, you care about approximation of the tree width, but don't you get also you have an effective.
So So for my result, I don't care about whether or not this is effective. Okay. And in fact, in our result, it won't be effective. So yeah, I'll say in a second. Okay, but I want to point out a corollary of this grid minor theorem. So one could use this grid minor theorem to prove a lower bound on the circuit size or AC0 circuit size of sub G for all graphs G via the following observation. I mean, so if you could prove that the subgraph isomorphism problem, just with respect to k by k grids, has circuit size n to the omega k for all k, then via this grid minor theorem and the minor-monotonicity of the subgraph isomorphism problem, it would follow that the G subgraph isomorphism problem has circuit size n to the omega tree width to some epsilon. Epsilon is 1 over c, in fact, for all graphs G. Okay? Similarly, you could put AC0 here and here. Okay, and if you did that, that would be, yeah. So this is, note that this is weaker than what we actually prove for AC0. We prove tree width over log tree width, but this would be another way of getting at least this result. So this is the strategy that we're going to use to get our lower bounds in terms of tree depth. Okay, and so this took, a new result in kind of graph minor theory. So, and this can be seen as sort of analog, sort of tree depth analog of this polynomial grid minor theorem. Okay, so I guess you could call this a grid tree path minor theorem. So this is joint work with Kenichi Korabayashi. So the result is the following, that every graph with tree depth, at least k to some constant c, contains one of the following three minors. So either a k by k grid, or a complete binary tree of height k, or a path of length 2 to the k. Okay, and each of these graphs has tree depth at least k. So therefore, these three obstructions are giving a polynomial approximation of the tree depth of G. Okay, so in other words, to compute the exact obstruction sets to tree depth seems like a hopeless task. There are doubly exponentially many of them. But if you only want the polynomial approximation of the tree depth, then you only these three classes of obstructions suffice. So that's what this result says. Okay, and similarly, as a corollary here, if you could show that the subgraph isomorphism problem for these three graphs has AC0 formula size n to the omega k for all k, then as a consequence that the G subgraph isomorphism problem would have AC0 formula size n to the poly tree depth for all graphs G in the same way. Okay? And this is what we do. So there, we have these three cases. So the grid case, in fact, follows from the previous work with Lee and Razbarov, simply because the k by k grid has tree width k, so it has AC0 circuit size n to the omega k. So therefore, it has AC0 formula size, at least that. The case of the path, this was shown in this previous work, which I mentioned. So this is really the distance 2 to the k connectivity problem. So this was in this previous work. And then the sort of only new ingredient is sort of extending this similar proof idea to work for the complete binary tree of height k. Okay, and this is unpublished. This is upcoming work, and I guess I should mention this. So this here was published as a SIG-log column recently, but it will be appearing in the next ITCS. Okay. Okay, so it's. These results, which give this, so the AC0 formula size of the G subgraph isomorphism problem is n to the poly tree depth. Okay. So in the kind of last part of the talk, let me tell you about the sort of surprising corollary of that result in finite model theory. So this is giving a sort of stronger, what I'll call polyrank version of the homomorphism preservation theorem on finite structures. So, I guess I have some time, so I'll try to go slowly here. So let me give the background, some of the background for this result. So here are three classical preservation theorems, and here I'm talking. This is sort of purely a model theoretic result, no assumption of finite structures here or anything. So, these. Here are three theorems, so the Voshtarsky theorem, Linden's theorem, and the homomorphism preservation theorem, which respectively say that if a first-order formula phi is preserved under injective homomorphisms, surjective homomorphisms, or all homomorphisms, well, so if and only if it's equivalent to a formula which is existential positive or existential and positive. Okay. Injective here really should be embedding, but ignore that. So these are results which sort of say that a certain semantic property of first-order formulas is equivalent to a syntactic property. Okay. So, one of the sort of early directions of research in finite model theory was exploring which theorems of classical model theory survive when the statements are restricted to finite structures. And some of the first results in that direction were showing that these preservation theorems fail on finite structures. So there are counterexamples to the Voshtarsky and Linden's theorems due to Tate and Aitai and Gurevich. So these counterexamples show that there exist first-order formula which is preserved under injective or surjective homomorphisms on finite structures, yet is not equivalent on finite structures to any existential or respectively positive formula. Okay. And in fact, yeah, there's a sort of, at least the Itai-Gurevich theorem, really it's even in a stronger form with respect to non-uniform AC0 circuits. So this is showing that the syntactic class of monotone AC0 circuits is not equivalent to the semantic class of AC0 circuits which compute monotone functions. So syntax is different from semantics with respect to monotonicity in AC0. And I guess I thought I had it on these slides, but I guess I don't. So yeah, I should have mentioned earlier that the proof of this result, used the compactness theorem of first order logic, and the compactness theorem fails in the finite setting. Okay, so an early result of mine, sort of before I was working in circuit complexity, was showing that sort of in contrast to the Voshtarsky and Linden's theorems, this homomorphism preservation theorem turns out to survive on finite structures. So the result is that if a first order formula phi with quantifier rank k is preserved under homomorphisms on finite structures, then it's equivalent on finite structures to an existential positive formula of quantifier rank f of k, where f is some computable function. Okay? So it's computable, but it's a very bad function. So this is actually a non-elementary upper bound on the quantifier rank blow-up. Okay. Now, in the same paper, we actually prove that, well, in the infinite, so we also give a new compactness-free proof of the homomorphism preservation theorem via sort of a constructive method, which actually shows that you have no quantifier rank blow-up in the infinite setting. So I call this the equirank homomorphism preservation theorem, that if a formula's, if a first order formula phi is preserved under homomorphisms, then it's equivalent to an existential positive formula with the same quantifier rank. So there was this big gap. In the finite setting, we had a non-elementary upper bound, and in the classical setting, we have the exact same quantifier rank. So this is a question that had been open from that work. So the new results of the improvement that we get, we actually using our lower bounds for formula AC0 formula size of subgraph isomorphism, we're able to show a polynomial upper bound on the quantifier rank blowup in the finite homomorphism preservation theorem. Yeah, so that's the. And so the proof is via, it's not that complicated, but it gives a reduction to this formula size lower bound, as I mentioned. Just a few other comments on this. So using just the lower bound for distance k connectivity, due to the fact that the length of the longest path in a graph is an exponential approximation of the tree depth, if you only appeal to this lower bound, then you would get an upper bound on this quantifier rank blowup of exponential in k. And if you take this simple reduction, and in fact you appeal to a lower, the very first AC0 circuit lower bound for the distance k ST connectivity problem due to Itai in '89, then you actually get also a non-elementary upper bound on this f of k. But the point is that actually, if Itai had noticed this simple reduction way back in '89, then the homomorphism preservation theorem wouldn't have been an open problem when I got around to thinking about it. It's nice that Itai misses a few things. But to mention that actually,
How bad is this polynomial?
What's that?
How bad is the polynomial?
So, okay, if you use in our theorem, as I stated it, it looks like we're using the grid minor theorem. So you'd incur their constant and you'd get some 86 or something like that. In fact, in the real result, the grid case is really a tree width case. So it's really something like 5 or 10 or something like that. But I mean, it should be. I suspect it should really. There should be no blow up. But I have no idea how you'd prove that.
With what formula size?
No, yeah. So I believe that the tree depth. So yeah, I strongly believe that n to the tree depth is the true lower bound. And in fact, I should mention that not only for AC0 circuits, but not only for AC0 formulas, but for general Boolean formulas. It's just that the proof technique somehow uses the fact that we're in the constant depth regime. So in addition to this quantitative improvement, I should mention that there's also the route via circuit complexity gives a sort of qualitative improvement that actually we kind of get a non-uniform circuit version of the homomorphism preservation theorem. And this is also in contrast to the Itai-Gurevich result, which showed that syntactic monotonicity is different from semantic monotonicity with respect to AC0. Well, here we show sort of that, so the semantic class of homomorphism preserved graph properties that are definable in AC0 coincides with the sort of syntactic class of existential first order logic, which is contained in polynomial size monotone DNF formulas, so just depth 2 formulas. So
what happens to uniformity here?
this is this is even non-uniform.
Right, so what is the existential positive FO?
This is just what you think it means. This isn't circuits.
Oh, okay.
Yeah, I mean, yeah. There's no what is a syntactically homomorphism preserved AC0 circuit.
Right.
So monotonicity is a nice thing because it's just no negations. But so anyway, the takeaway is that if you take this powerful class non-uniform AC0, and if you restrict to just the homomorphism preserved properties, then this class collapses to uniform polynomial size monotone DNF. So this question of syntax versus semantics. We had all these counterexamples, but maybe there's some evidence that at least for a very strong property like homomorphism preserved, that these things actually coincide. So here's the last slide. So sort of summary. So we introduced this subgraph isomorphism problem, this nice family of problems, and showed that so its complexity is tied to natural structural parameters of G, and to fundamental questions in complexity theory, P versus NP, L versus NL. So we went over this nice connections between AC0 and first order logic, and sort of the maybe main takeaway is that AC0 circuit size is related to the first order variable width, which is related to the tree width of G, and formula size is related to quantifier rank and tree depth. I showed you that for this colored problem, there's this really nice natural family of input distributions, x sub beta, and it's sort of remarkably, for sort of optimal choice of beta, this sort of these turn out to be sort of hard on average. So, that's the last slide. I never know how much ground I'm going to be able to cover, so I prepared a few extra slides after the thank you, which maybe I have time to show a little bit of. Maybe people want to get out early, but okay. Maybe I'll end it here and we can take off. Yeah.
I'm intrigued with this connection using specialized average case for the worst case. Is it a unique occurrence, or this technique is quite common?
No, I don't know. Yeah, I don't know of another result. So so we're kind of looking at the worst average case complexity, right? I don't know other results that actually work that way.
That seems to be the most intriguing part in the whole.
Yeah. So here's a question I really like. I mean, we know that semantic monotonicity is different from syntactic monotonicity, not only for AC0, but also for formulas, also for circuits. Okay, so there exists Boolean functions which have there exist monotone Boolean functions which have polynomial size non-monotone Boolean circuits, but require exponential size monotone circuits. So there's a huge gap, but so far as I know, there's no known gap in the average case with respect to a product distribution. Okay, you can make artificial distributions where you have a gap. And I'm very tempted to conjecture that actually that there's no gap. So, if instead of product distribution, or let's say uniform distribution, if you say the slice distribution, so the uniform distribution on inputs of Hamming weight exactly n/2, then there's no gap. Monotone and non-monotone complexity coincide. So this is a very curious thing. So I think it's sort of evidence that, if you look at the uniform distribution, which is, morally speaking, similar to this, slice distribution, maybe monotone and non-monotone complexity coincide there. So that's something I've been very interested in.
Thank you very much.
Are there questions or a desire to see the further slide?
That's all. I think it's...
We'll put them online.
Okay.
Yeah, okay.
Thanks.
Thanks.